Hello, students. Let's learn something new today. How about Lemberts principle? This Lemberts principle is a part of Module 5 of Elements of Civil Engineering and Engineering Mechanics for the first year of any engineering branch. So, what is this Lemberts principle? Now, we all know the principle is based on a person's thinking, and that person's name is Lambert. So, who is this Lambert if we try to understand? So this person is D'Alembert, or his full name was John Leron D'Alembert, who was a French physicist and a mathematician. So what did he think of? So let's understand that by taking a small example. So what if your car is broken down and you're trying to push it? So if you rewrite it as a free body diagram, it is a body with mass m having a force F, which is being pushed by an acceleration A. So from Newton's second law of motion, we know that F is equal to ma, where F is the force, m is the mass, and a is the acceleration. Now what if the same car is being pushed by two people? So if we rewrite the free body diagram again, so we have the body of mass m, but here there are two forces, F1 and F2. Now, if we consider that being pushed with the same acceleration a, it has a resultant of r. So if there are a number of forces acting on a body, then the resultant force can be considered. That is, I can rewrite the Newton's second law of motion statement as r is equal to ma, where F is being replaced by the resultant of forces. This particular equation can be rewritten as r minus ma is equal to 0. This particular equation forms the basis of D'Alembert's principle. And this also takes into account the amount of force that inertia causes. That amount of force that inertia causes is nothing but your mass into acceleration. So that is your inertia force. And it is also considering something known as dynamic equilibrium, because something is in motion, right? So it is dynamic. That is dynamic equilibrium. So hence, if we consider this D'Alembert's principle statement, we know that the resultant of the system of forces acting on a body of mass m and with acceleration a is in dynamic equilibrium with inertia force ma applied in the reverse direction of the motion. Mathematically, it is nothing but net accelerating force minus inertia force is equal to 0, or r minus m is equal to 0, the same statement which we understood previously. So if we are trying to apply this particular principle to some problems, let's understand what kind of problems exist. There are two types of problems. One, the lift or escalator problems. Two, on various other type of bodies. So let's understand the type 1 problems in this particular video. Type 2 we'll understand in the next video. So what is this type 1 problems? So before we start solving these kind of problems, we need to understand the different situations of the operations of the lift. So if we consider the free body diagram of the lift, it would look something like this. There is a system of forces. It is being connected by a spring scale. That spring scale is being connected to a string, and that string is the connection between the spring scale and the object or the box in which we move around. Now in this particular thing, let's consider T to be the tension in the string and W to be the weight of the box. So different cases of lifts exist. So the first case being lift at rest, or it is not moving. If the lift is at rest, then we know that acceleration is equal to 0. Or the free body diagram can be written like this, where W is acting downwards and T is acting upwards. So if we consider sigma V is equal to 0, then we get T is equal to W. The similar case if the lift is moving with constant velocity. So we have acceleration to be equal to 0 and sigma V is equal to 0 will give you the same equation, T is equal to W. How about case 3, where the lift is moving upwards or lift is accelerating upwards? So if we consider the free body diagram of it, you can see that there is a weight of the box acting downwards, tension acting upwards, but here the lift is moving upwards, and hence there is an opposite force, which is MA, that is your inertia force acting in the opposite direction. So if we consider sigma V is equal to 0, T minus W minus MA is equal to 0 is what we get. If we rewrite that, we get T is equal to W plus MA, or T is equal to W into 1 plus A by G, where the mass is substituted as weight by acceleration due to gravity. So here, if we consider lift accelerating downwards and we have the free body diagram, you can see it is moving downwards, and hence there is a inertia force which is moving upwards. So again, if I consider sigma V is equal to 0, T minus W plus MA is equal to 0, which is what you'll get. That is rewritten as T is equal to W minus MA, or T is equal to W into 1 minus A by G. Now, applying these problems to various practical problems, let's take the first question. A lift carries a man of weight 4000 Newton and is moving with a uniform acceleration of 3.5 meter per second square. Determine the tension in the cable when the lift is moving upwards, the lift is moving downwards. So let's understand what's been given. It has been given that W is equal to 4000 Newton and A is equal to 3.5 meter per second square. Let T be the tension in the cable. So the first case, when the lift is moving upwards, we write the free body diagram, and we know that sigma V is equal to 0, or T minus W minus MA is equal to 0, which can be rewritten as T is equal to W plus MA, or T is equal to W into 1 plus A by G. If we substitute all the values that we know, we would get T is equal to 4000 into 1 plus 3.5 divided by 9.81. Here, acceleration due to gravity is considered to be 9.81 meter per second square. So we get an answer of 5427.12 Newton of tension in the string. When the lift is moving downwards, whereas then if I consider the same free body diagram, then you can see the lift is moving downwards. So there's inertia force which is moving upwards. So sigma V is equal to 0 and T minus W plus MA is equal to 0, which would give us T is equal to W minus MA, or T is equal to W into 1 minus A by G. If we substitute all the values that we know, then it is T is equal to 4000 into 1 minus 3.5 divided by 9.81, which would give us an answer of the tension of the string to be 2572 Newton. Let's understand other type of problems in the next video. Until then, thank you.